through these discussion questions dealing with air resistance. All right, so the first one says, a tennis ball dropped from rest at the top of a tall glass cylinder. First, the air pumped out of the cylinder and there is no air resistance. And then a second time after air has been readmitted to the cylinder. You examine multi-flash photographs of the two drops. From these photographs, how can you tell which one is which? Okay, so at the start, so if it is a very short tube, it is going to be tough to decipher which is which. At the start, when the velocity is 0, the acceleration of the no air tube is going to be g, and it's going to be that the whole time. At the start, when the velocity is 0, the acceleration is still g, because this v term is 0. And so they actually start out with a pretty similar acceleration for that first strobe, that first time section. You might be like, wow, they look the same to start out with. But as this v value gets bigger as it falls, this term itself gets bigger, and so that acceleration really starts to drop off. And eventually that acceleration will become 0. It will reach its terminal velocity, and then the distance between those dots will end up being the same. So you really want to look at the bottom of those pictures to see which one is accelerating more. That's going to be the no air, and which one is accelerating less. That's the one with air. All right. The second one says, you throw a ball straight upward. If air resistance is not ignored, how does the time required for the ball to go to a height at which it's thrown up to a maximum height compare with the time that it takes to come back down? Okay, so the time up versus the time down. Now, if air resistance was negligible, meaning that V naught and V are the same, it's going to take the same amount of time to go up and back down. However, in our scenario, we're losing energy on the way up and on the way back down. So I start out with a much faster velocity than I end with. And so the time it takes for me to go this distance with higher velocities is going to be smaller than the time it takes to go the same distance, but now with slower velocities. And so yeah, time up will be shorter than the time back down. Okay. Third one here. You take two identical tennis balls, fill one with water, and you release the balls simultaneously from the top of a tall building. If air resistance is negligible, which ball strikes the ground first? Well, if air resistance is negligible, the masses cancel. It didn't matter which mass they had, and the acceleration is g. They'll reach the ground at the same time. What is the answer if air resistance is not negligible? Okay, so now they have the same b value. They have the same shape. They have the same outer coating. So all that stuff is going to be the same. So its b value is going to be the same. The difference now is mass. So if I go ahead and set up that equation, so I just chose bv. It might be bv squared, or might be a squared one here instead of a singleton, but I chose the single. And so I'm just going to divide everything by mass. And so this is the term I'm really concerned about. And so they have the same b value, but they have different masses. And the one with the larger mass here, the more dense object, is going to have a much smaller effect from friction influencing its acceleration. So the larger m is going to have the smaller frictional term here. Therefore, it's going to end up with the larger acceleration, so that water-filled one is going to reach the ground first. And that's just generally true, like if you drop a hammer and a feather, the more dense object is going to have a larger acceleration. And then the last one here says, a ball is dropped from rest and feels air resistance as it falls. Which of the graphs best represents that function? Okay, so stealing this same function we just came from here, as it falls, as V increases, this resistive force gets bigger and bigger. And this term gets to the point where eventually it equals G, because at that point the acceleration is 0 and that V value can't get any bigger. And so what we'll see is as that V increases, the acceleration approaches 0. And so the best graph for us here is D.